A very good morning, a very good evening to you guys. So like we said, right, welcome to this series of cross night lessons, right? It's a master class for Euclidean geometry. From grade 10 to 12, when you look at Euclidean geometry, right, grade 10 focuses more on like quadrilaterals, right, giving you the properties of parallelograms, rhombus, kites, and the likes, which is a very good solid background for later on questions, right? But then grade 11 focuses on circle Euclidean geometry, right, whereby we're talking about theorems that are related to a circle. And then grade 12, we are talking about theorems related to triangles only. So it means grade 10 is quadrilaterals, grade 11 it's circles, grade 12 it's triangles. And then in most of the problems that you're going to see, they combine everything. That is what makes Euclidean geometry special, because it's a combination of different sections. My name is Mr. You can see, so we're going to start now and look at the 6 examinable theorems proofs in grade 12. We're only proving 6 of them, so these are what we have here, right? I'm hoping that you are able to see, and this is what we have in terms of the proofs. Right, you're able to recognize them, right? That's good. So you see the first one here, this one, if you can still remember, this is talking about that the angle subtended at the center is twice the one at the circumference. Remember this one, this is a tangent, so this is the Tan-chord theorem, right? And then you should also remember this one. It's related to it's related to cyclic chords. So it says that when you add these two, you get 180. When you add these two, you get 180. And then this one here is the first theorem in your textbooks, right? Which is talking about the perpendicular line that bisects the chord, okay? And then this one, if you can remember, this is from grade 12 now, the proportionality theorem. And then this one, whereby you see 2 triangles, that's the similarity theorem. Okay, so diving into the first one. The first theorem says the angle subtended by a chord at the center of a circle is double the angle subtended by the same chord on the circumference. I tried to highlight the most important parts about this theorem, and those parts are: the first one is that we are subtending an angle. The word subtended in terms of Euclidean geometry, it simply says you are forming an angle from 2 points. That is the word subtended. So if I'm saying the angle subtended by a chord at the center, I mean that I have a chord here. A chord might not necessarily be drawn. Like, you don't have to really draw a chord here so that I can call it a chord. The fact that I have points M and K, if I were to join them, I would have a chord, isn't it? If I can join them like this, I would have a chord. So you should, this theorem, you can say the angle subtended by a chord, or you can say the angle subtended by 2 points. But it doesn't sound nice. So we'll use a chord. So essentially though, you have to have a good understanding of what is an angle. What is an angle, good people? Maybe if I can start there. What is an angle? That is a good definition of what is an angle. An angle is indeed a space between 2 lines that meet at a point. So if 2 lines meet like this, that is an angle. If I have a triangle, right, and then I have these 2 lines here, this one and that one, they meet at this point, so it means that this is the angle here. That is the space between them. Now that space, we measure it in degrees, okay? And then here we also have a space between 2 lines that meet at a point, so it's an angle again. Even here it's going to be an angle. Now if I can name it A, B and C, let's be careful in terms of the notation. This angle here, I am allowed to call it angle B. When I'm saying angle B, I'm saying it's the whole angle here. Okay, now I can also call it angle A, B, C, right? But then I put this small cap on the letter in the middle to indicate that this notation, what it means is that you have line AB, which is this line. Let me try to show with a different pen. It means you have line A, B, right, which is this line, and then you have line what? You have line BC, which is this line. Okay, and then in the middle on B there, in the middle you are forming the angle. Okay, in the middle you are forming the angle. So as I'm saying, right, this angle here, we can call it angle ABC. Okay, that would be our angle there. Let's look at the other one. This angle here, I'm allowed to call it angle A, or I can also call it what? Angle BAC, and then I put the cap in the middle to indicate that the lines that are making up the angle, it's BA and AC. They are the ones making up that angle, angle A. Okay, and then this one I can also call it what? ACB, or I can call it angle C. But let me ask you something, right? Let's say I have O here, right? And then this is C, and then D, and then E, right? What would be this angle here? Let me call it O1 and then O2. How can we name this angle? Very much important to know how to label your angles. So O1 there will be OCD, and then O2 would be COE, right? Meaning O2 here, I can call it a COE, or I can also call it EOC, right? That is good. So that is the first thing that we needed to actually understand. Okay, that's the first thing we needed to understand. So from this, right, we are able to then prove our first theorem, right? As I said, we are going to prove 6 theorems, and then after proving them, we are going to look at papers, past papers that are asking about the theorems in terms of proving them, so that already you know that you have those 5 marks in the bag. All right, now the first one, as I'm saying, right, it says the angle subtended by a chord, which means, right, if I were to draw a line, like I said, on MK here, I would have a chord, and that chord would form an angle at the center, that is to subtend. That chord would form this angle here because it will be 2 lines. Okay, so that angle will be forming a chord. So let's understand that the one that is formed at the center here is going to be 2 times the one formed at the circumference. So the one at the center is always double the one at the circumference. Ne? I always say this. You can think of the center as your home. At home you get more love than outside. So you can think of at home receiving double amount of love than the one you get outside. You understand me? You get half love outside. I think that is very much true. So we have to prove that. So the proof, right? That is what we're going to look at. So now we have to prove. We have to prove that I'm gonna call them some names, good people, so that we know which angles we're talking about. Remember, on your diagram sheet, this is what is going to be given. The moment you get this, good people, please do this for me, right? The moment you get it, say, call this O1 and then draw a line there and then call this O2. Okay, so that you have O1 and O2. O2 is the one inside there, O1 is the one outside. And then after that, this one, obviously it will be, what would be this angle here? What would be the name of that angle? Since it is this one, we would call it angle L, or you can call it what? MLK, okay, because it's an angle formed by ML and LK. ML and LK. Okay, so that is the angle there. So we need to prove, right? We need to prove that angle O1 is twice angle L. Okay, that is what we need to prove. That O1 is twice angle L. Not O2, good people, O1. Right. So, in order to prove that, it's going to be very, very simple. I need you to, let me ask maybe one of you, which car do you like the most? Anyone who can tell me the name of their favorite car? I know I like
McLaren.
What?
A McLaren.
McLaren. Is that a car or it's a car? Excuse me. Oh, excuse me, guys. I don't know anything. I don't know much about cars. I think the only car that I know is one, because I usually use it in maths. Right. I only know Benz. That's the only car that I know, good people. And the logo of Benz, if you can check, the logo of Benz looks like something like this. That is the logo for Benz. Right. So why do I like this car so much? This is because in Euclid it helps me a lot, especially when proving. How does it help me? I usually just draw this symbol for Benz, and then I join it with some dotted lines here. I want you to see what actually we are forming. Do you see that I've formed 1, 2, 3 triangles? Let me try to zoom it if you can't see it properly. Right. Here's what we have here. So I like Benz because you can form some nice triangles there with that logo. Okay, so what you see here is what we are going to try and create here. How can we do that, right? We can do it in this way. Use a pink one. So we're going to draw a dotted line. We're going to try and have this Benz logo, right? You're going to draw a dotted line here. Right, now you have 2 triangles, but it still doesn't look like the Benz logo, So for it to look like that, you then join these ones. Right, and then you have formed it. You see how many triangles you have now? Now it means you have these triangles. You have this one here. Oh, sorry. You now have this triangle MOL, right? And then you also have triangle MOKM, and then now you also have triangle LOLK, right? That is a triangle you have. So you have formed 3 triangles. So whenever we are proving this theorem, let's remember Mercedes-Benz. Let's form 3 triangles. Now you are obviously going to tell the examiner what you just did there, because the examiner doesn't know much about cars, right? So what you can say to the examiner is the following. First of all, you're going to say, this is a statement you're going to, this thing, right? I don't know, sorry, can I just maybe move it somewhere here, right? And then remove this one, so that we always remember what we are working towards, right? Is to prove that O1 is 2 times angle L. Great. Now the first thing we're going to do is that because we have some dotted lines, you're actually going to show the dotted lines on your diagram sheet. Then you're going to say join, right? You're going to say join O and L, then join O and M, and then M. Oh, sorry, it's joining L and O, right? Let's just write it like this: join OL, O to L, and then join M to K. Right, let's write it like that: join O to L or L to O, and join M to K or K to M. That is what you're firstly going to write. You're going to get a mark for this because it's part of construction, but I'm not calling it construction because we are joining. We are not really constructing. Okay, after you have joined them, you tell the examiner the very same things you joined, right? OL, remember, OL now, it's actually a radius, because what is a radius? It's a line from the center to the circumference. So this is actually a radius. This is also a radius here, and then this is also a radius. Okay, so we firstly tell the examiner that OL is going to be equal to OK and also equal to OM. Why? Because these are radii. That is first thing you're going to tell the examiner. So please know, good people, always remember that because you have a center, this line is going to be equal to that line. It's also going to be equal to that line. Good. Now the second thing now is to do what? You are now going to say, because you have the lines being equal there, right? Let's remember that in triangles, we have this special property for triangles. Remember back in grade 3, you used to talk about this triangle here, which you call an isosceles triangle. This triangle is an isosceles triangle, is a triangle with two sides that are equal. So let me just call it A, B, C. If the two sides are equal, let's know that these angles that are opposite the equal sides, these angles that are opposite the equal sides, they are also going to be equal. Okay, so if AB is equal to BC, then you are going to say that angle B will be equal to angle C. What will be your reason? Your reason will be angles opposite equal sides. Okay, angles opposite equal sides, because those are angles that are opposite the equal sides. Grade 9s know this as base angles, but as we use this reason to say angles opposite equal sides. Hope you got that. Okay, we can try it with others just to see whether we really understand that. I can have another triangle here. Let me just put it maybe like this. Yeah, I think it should be good like this. And then let's say this side is equal to this side, and then I'll call this A, B, C. Or maybe let's call it a triangle K, F, C. Good people, which sides are going to be equal? We can see that KF is equal to KC. So which angles are going to be equal?
F and C.
That will be angle F and C, right? Angle F, which is this one, would be equal to angle C, which is that one, because those are the angles that are opposite the equal sides. They are facing the equal sides. Okay, so you write that these are angles opposite equal sides. Great stuff. Okay, so I hope that we're still together there. That is how we can identify the angles that are opposite equal sides. But maybe can I also maybe ask, right, to say, what if, right, what if I had something like this as my triangle? I had this, and then let's just call it also triangle K, F, C, and then it so happens that here I know that this is 45 degrees, and then there it is 45 degrees. What can you say about the lines FK and KC? What can we say about those lines?
Wow.
The lines are going to be equal, right? So we're going to say FK will be equal to KC. What would be our reason? We can't say angles opposite equal sides.
Want to be angle opposite. Side opposite angle.
Because those are the sides that are opposite the equal angles, right? Those are the sides that are opposite the equal angles. So KC must be equal to FK. This is actually one of the ways of proving that lines are equal. If they ask you in a question in Euclid to say prove that FK is equal to KC, always check that can you not prove that this angle is equal to that. If you have proved those angles are equal, it means the sides should be equal. Okay, but why was I bringing this into the picture? This is because in terms of what we have here, right, let's understand that if I have this triangle like this and then OL is equal to OK, that should actually mean that here, if I can have an angle X, it means also here I'm going to have angle X. Those angles are going to be equal because the opposite, because the sides are equal, right? So what I need you to do for me, right? Remember I said you should have O1, O2, also have O3, ne? And then after that I need you to have L1, L2. I also need you to have K1, K2. Also you should have M1 and M2. All the time when you get this triangle, after making the Mercedes-Benz triangles, right, make sure that you have you just make circles on the angle so that you have L1, L2, K1, K2, M1, M2. Then I need you to then say X and X, and then here Y and Y, isn't it? Use a different one. So here we're gonna have Y and Y. Remember the sides must be equal because the angles must be equal because the sides are equal. And then after that you're going to have W, or you can have Z, ne? And Z. So you're gonna have X, Y, and Z. Beautiful. Now you're going to tell the examiner that I have those things. I have those things. So you're going to say let, right? So you're going to say let angle L2 be equal to, let me write it nicely here. Let angle L2 be equal to angle K1. L2, let it be equal to K1, and both are going to be X. Why are you saying that? Because these are angles opposite equal sides. Right. Then you're going to say K2 must be equal to M2, and both must be Y. Why are you saying that? Because those are angles opposite equal sides. Right. And then you're going to say M1 is going to be equal to L1, and both will be Z. Why? Because those are angles opposite equal sides. Right. And then after having those, right, after having those, you're going to say, okay, because, by the way, I like this method because it's going to be very much similar to all the other theorems that we're going to prove. So this part will most likely be the same for the 4 theorems we're going to prove. Okay, what is only going to change is the next part now. The next part now is going to be dealing with the theorem in question. The theorem has to prove that O1 is equal to 2 angle L. We have to prove that O1 is equal to 2 times angle L. Now you're going to say, where is O1? This is where O1 is. Now O1 is in a triangle, right? So you can tell them that in triangle what? OMK. In triangle OMK, ne? If we were to say angle O1 plus angle K2 plus angle M2, you would get what? You would get 180 degrees. And then what is your reason? Do you still remember what is the reason for us adding angles in a triangle and saying they must be equal to 180?
Sum of angles in a triangle.
Perfect, because those are the sum of angles in a triangle. Those are some of the interior angles in a triangle. So we say O1 will therefore be plus what? K2 is a y, and then M2 is also y, is equal to 180 degrees. Then you say therefore angle O1 will be equal to 180 degrees minus 2y. Good. Now you got the expression for angle O1. Right. You have the expression for angle O1. But you are not done, right? You only got O1. So you also need to get the other ones. Good people, after this step, right? Remember that here I added angles in the smaller triangle OMK. The next step is to add the angles in the bigger triangle, the Mercedes-Benz triangle. Please, good people, remember that. Ne? So what I'm going to do is that I'm going to remove the top part. I'm hoping that you have it with you there, right? Yeah, I have to remove this part. I'm hoping that you have. Right. Now that we have O1, ne? Let's add all the triangles in the bigger triangle, in that big triangle. So you're going to say in triangle MLK, ne? Angle M plus angle L plus angle K. Remember, M is the whole angle, L is the whole angle, K is the whole angle. They must also give us 180 degrees. Why? Because these are sum of angles in a what? In a triangle. So angle M is going to be Z plus Y. Angle L is going to be what? Z plus X. And then K is going to be what? X plus Y. In simple terms, you're always going to have 2x plus 2y plus 2z being equal to 180. Why? Because z and z is 2z, x and x is 2x, y and y is 2y. So after having this step, you are always going to have a step whereby you have 2x plus 2y plus 2z. Good. Now, you see that here you have 180 minus 2y, ne? Right, check here. You have 180 minus 2y. And then here you have 180, and then there is 2y. So what is the next step? Is to make sure that you take that 2y there, and then you take it to the right. Okay? You take it to the right. So if you do that, what you're going to have is 2x plus 2z being equal to 180 degrees minus what? Minus 2y. Great. And then now that you are here, please just take the common factor here, 2. So if you take 2 as a common factor, you simply have x plus z being equal to 180 degrees minus 2y. Wait, what is x plus z? Zoom into your triangle. Can you tell me which angle is x plus z? Is it angle M, angle L, or angle K?
L.
Perfect, it's angle L, x plus z. So therefore, 2 angle L is equal to angle O1. Then you have proved it. Right, then you have proved it. So what is the procedure? Let's always remember that the procedure is very simple. Number 1, you join the radii. Ne? I'm writing this as some notes you must have as we go along. You join the radii. Then after joining the radii, what do? And for you to join the radii, remember your Mercedes-Benz. Good. And then after that, after joining the radii, what do? We then label, right? we make sure that we label X, Y, and Z on the angles that have been formed, right? And then after labeling the X, Y, and Z angles, then what do we do? Make sure that you tell them, right, you're going to use these angles opposite equal sides. You're going to use that rule, because you'll just be telling them that K1 and L2 both are equal to X, angles opposite equal sides. K2 and M2 are equal to Y, angles opposite equal sides. M1 and L1 are going to be Z, angles opposite equal sides. And then after that, what do? You add, or rather you find O1 by using that smaller triangles, meaning by using sum of angles in a triangle. Then lastly, you add this one. I'm gonna write it in orange. Add angles in the bigger triangle. Please add angles in the bigger triangle. This is the step here. After adding the angles in the bigger triangle, you make sure that you have, since you had 180 minus 2y, make sure that you have it this side, and then you take out a common factor, then you'll be good. So please, let's remember those mini steps that we must follow there. Let's remember those mini steps that we must follow. Okay, so we essentially join the radii, label X, Y, and Z, use angles opposite equal sides, and then say angle O1, right, that. I don't know if maybe, let's see, I'm contemplating between going to the question or going to the next theorem. But let's go to the next theorem. Good people, by the way, right, I wrote that in short, right, when you are going to be using the theorem, you simply say angle at center is equal to 2 times angle at the circumference. So let's remember that when you are now using the theorem, you're going to be saying angle at center is equal to 2 times angle at the circumference. Are we all good here? Any question? Okay, so we can continue to the next one. Now here's theorem number 2, right? What does theorem number 2 say? It says that the angle between, right, the angle between a tangent and a chord is going to be equal to the angle subtended by the same chord on the circumference. This is your Tan-chord theorem. Okay, so what it says is that here is a tangent here. You would be given that this is a tangent. The angle between the tangent and the chord is this one here. Right, this is the angle between the tangent and the chord, because the chord is TK, right? The chord is TK, and then the angle between the tangent and the chord is T1. So the angle subtended by that chord on the circumference, it's going to be what? It's going to be angle J, so it will be this one here. Okay, so what we need to prove, right? What we need to prove is that angle T1 is equal to angle J. That is our goal. So how do we do that, right? Do not worry, do not think a lot, just think about Mercedes. So what you will do is that you're going to have to construct your lines, okay? So you're going to construct a dotted line here, then construct a dotted line here, and then another dotted line here. Then you have your Mercedes, right? Then after doing that, so you're going to tell them here that join the following: join OJ, join OT, join OK. Okay, then you're going to tell them that just like in the previous, OJ is equal to OT is equal to OK. Why? Because all of them are radiuses. Okay, then what do we do from there? Label them. Okay, just go back to your go back to your angles here, then you're going to label them. So this is T1, you're gonna call this T2 and then T3. This one you call it J1 and J2. This one you're gonna call it what? K1 and K2. Whichever way, even if you can say here it's 2 and then 1, the theorem you always be able to prove, okay? Whichever way, do not worry. Right, and then here let's remember that this line is gonna be equal to that line, they're going to be equal to that line. So here we must have O1, we must have O2, and then we must have O3. That is the first thing you do there. Right, then after that, what do we say? Let's have our x. So you say x, x, y, y, and then z and z. Right, maybe if the I'm hoping my z is visible. I know my z is not always nice, but that will be z there. Or if maybe z is not doing the things for you, you can use w. I think w is also nice, so you can use w there. X, y, w. Most people prefer z because they know I'll just be saying x, y, z, but you can also say x, y, w. Okay, so let's remember that O2, it's essentially going to be 180 degrees minus 2x. O1 is going to be 180 degrees minus 2y. And then O3 is going to be 180 degrees minus 2w. Perfect. You just need this. Then you go here. Then you tell them that let angle T2 be equal to angle K2, and both should be x. You tell them angles opposite equal sides. And then you tell them again, let angle T2, K1, right? Angle K1 be equal to angle J2, right? Both will be y. You tell them angles opposite equal sides. And then again you tell them J1 must be equal to T3 and both must be w. You tell them angles opposite equal sides. Perfect. And then now that we have this, what is the next step, right? We then say, okay, you can see that this part is exactly the same as the previous part for the other theorem that we were proving. But now it's going to be different on this case, right? Where is it going to be different? If you can remember on the previous theorem, right, when we were proving it, we then went to O1, isn't it? We went to O1 first. So that is the same thing we're going to do here. We are going to go to what? To T1. Where is T1? Here is T1 here. Perfect. Since T1 is there, we need to find an expression for T1. Remember, to get O1, it was easy because we just added the angles in this triangle here, in this triangle, right? We added the angles here, then we were able to get our O1 as 180 minus 2y. However, how do we get T1? We need to invite a theorem that I'm hoping that we know. We need to invite this theorem. Do you remember that if you have a circle and then a center, and then you happen to have a tangent, because GTH is a tangent, do you remember that it's 90 degrees here because this is a radius? And we usually say that the reason is tan perpendicular to rad. So it's always going to be a 90 degrees between that tangent and the radius. And then this is your reason, okay? So that is the theorem we are going to borrow in order for us to have what? In order for us to have an expression for T1. So we are going to say, we know that OTH should be what? 90 degrees. OTH should be what? 90 degrees. So there, I'm going to put it with a nice color to remind us that actually here it's a what? It's a 90 degrees. And then what is your reason? Your reason would be tan perpendicular to rad. That is the only way you can get the expression for T1. So OTH is made up of what? Of T1 plus T2. Do we agree with that? OTH is made up of T1 and what? And T2. So that means that T1, we're going to have T1 plus what? Plus X being equal to 90 degrees. Therefore, your angle T1 will be 90 degrees minus what? X. Then you have the expression for T1. Good. Now what is the next step? The next step is to get the expression for J. And how do we do that? If you can remember for the previous theorem, for us to get angle L, we added the angles in the triangle, the Mercedes-Benz triangle. That is exactly the same thing we're going to do here, good people. So we're going to say in triangle JTK, in triangle JTK, you're going to add angle J plus be careful now, plus JTK, okay, plus JTK, because it's going to be JTK. We're talking about this angle here, this one, okay, this one. So it's JTK, right? And then we say plus what? Plus angle K, because angle K is the whole angle, right? If we had said here just angle T, we would be talking about the whole angle, so hence we didn't say that. And remember, it must give us what? 180 degrees, our reason, sum of angles in a triangle. I'm just squeezing it there because I don't have space. Right, angle J, remember it's going to be W plus Y, plus angle JTK is going to be W plus X, and then here you're gonna have X plus Y is equal to 180. Good people, I told you that you'll always have 2x plus 2y plus what? Plus 2z. But in this case, it's w, right? So we're going to say plus 2w. Then, remember, you need to ensure that you have 90 minus x, just like the previous theorem. Remember that here we needed to make sure that we have 180 minus 2y, because here we had 180 minus 2y, right? So for us here, we're going to make sure that we have 90 minus x from this. And the only way to get 90 here is if you divide by 2. So you have to start by dividing everything by what? By 2. So that you have x plus y plus w being equal to what? 90 degrees. Remember, you need 90 minus x. So you're going to take this x to the other side. You're going to have w plus y being equal to 90 degrees minus what? Minus x. Can someone tell me which angle is w plus y?
J.
It's angle J, right? It's angle J. That is w plus y. It's angle J. So angle J is 90 degrees minus x. What do you know? So therefore, you conclude to say angle T1 is equal to angle J. You have proved the theorem. Beautiful stuff. The reason why I specifically said let's start with proving the theorems, I want you to know this way of proving the theorems whereby you won't have to worry about using other theorems to prove a theorem, right? Yes, I know here we used other theorems to prove a theorem, but it's only going to be one. It's only this case, good people, okay? But you can see that it's going to be a routine, something that you're going to get used to very, very fast, okay? So you're going to be fast with it again, right? All the time, you must have this part, and then after having this part, you remember that I'm working with which theorem now. If I'm talking about a tangent, I have to remember tan perpendicular to rad, so that I can have expression for what? For T1. And then after that is the routine. You are adding angles in the bigger triangle. And then after adding the angles in the bigger triangle, you just have to manipulate them so that you have 90 minus x. And how do you do that? You just do that by simply dividing by 2 throughout, and then taking your x, say come here, and then it is this side. By just doing that, you are done because x plus y is going to be your j. By the way, if it so happens that because of time you couldn't continue on this step, you are going to get full marks by just writing x plus y is equals to 90 minus x. You get full marks because you have proved the theorem. Okay, that is why I like this way. And then same thing this side. You just say, no, I have 2x plus 2y plus 2z is equal to 180, right? But I need to have minus 2y. Just say 2y come this side, it comes this side, and then what you have is 2x plus 2z. The only thing is that you have to take out 2 as a common factor so that you are left with your angle L. Your angle L is x plus z. Then you are done. Right. Good. So I hope that you're okay. So let me just quickly send you a new link and then we continue on this next session. Let's move on to the next one, which is theorem 3, right? Now this one is talking about a cyclic chord. Now the theorem says that the opposite angles, right? The opposite angles of a cyclic chord, they add up to, they are supplementary, which means they add up to 180 degrees. I could not put a degree there, I had to write it by words, but they add up to 180 degrees. So when you're using the theorem, or in short, we're just saying that the opposite angles of a cyclic chord are supplementary, but you write it like this when you are using the theorem, which is what we are still going to go through during this what you call cross night. I hope you're not sleeping, guys. Can you just maybe put some emojis there so that I can see people are not sleeping? Right, now let's go to this theorem. This one we can see that we don't really we can't really form the Mercedes-Benz logo here, good people, because the Mercedes-Benz logo, remember, it's talking about 3 triangles and it will be something like this, like this. But here we can't really have that. So what we are going to do, do not worry, what you're going to do is that you are going to construct, meaning you're going to have your dotted lines. All of the dotted lines must go to the center, good people. Please, all of them must go to the center from each corner of the cyclic chord. Just do this for me. So for a cyclic chord, because we're talking about a chord, remember chord means 4. So we're going to be working with 4 triangles. Okay. So so we're going to be working with 4 triangles. Now after doing this, just like the previous ones, already you label them. Okay, I'll label this T1 and T2. I'll label this what S1 and S2. Then I'll label this R1 and R2. I'll label this P1 and P2. I'll label this O1, O2, O3 and O4. It doesn't matter whether you put 1 here and then 2 there, as long as you have O1, O2, O3 and O4. Right, after doing that, good people, let's remember, right, let's remember that OP is actually a radius because it's a line from the center to the circumference. So O1, OR, OS and OT are going to be equal. Okay, so after that, because the sides are going to be equal of those triangles, they are going to be isosceles triangles. So the angles opposite the equal sides must be equal. So you can just have X, Y, Z. Now I'm going to use Z, good people, because I'm going to have Z and W. Okay, I'm going to use Z and W. Whichever letters you want, good people, you can use them. If you feel like my name is Vanessa, I'm going to be using VV. NNEE. It's up to you. Okay, so now that you have this, right, then what are we going to say? You are going to tell them what you just did. Remember, the examiners are slow learners, right? So you are simply going to tell them here that oh, by the way, before I forget, since we said the theorem says that the angles of opposite angles are supplementary, it means we need to prove that angle P plus angle S is equal to 180 degrees. The theorem says you must prove this. Prove what the theorem is saying. Okay, so remember, the first thing you tell the examiner, right? They are slow learners. Tell them join. join what? Join OP. This is my P, by the way. I know it doesn't look like a P, but it's my P there. Let me just write it nicely. This is P here, right? OP, and then OR, and then OS, and then OT. By the way, what you just wrote here, you come back and say OP must be equal to OR, must be equal to OS, must be equal to OT, and then you just say radii. So you can see for these theorems, proving them, you're not thinking too much. What you wrote is just what you say they're equal. And then after that, what do you say, right? Like we did in the previous ones. You're just going to say, let angle S2 be equal to angle R1, and both must be X. Then you tell them angles opposite equal sides. Then you tell them angle R2 must be equal to angle P2, and both must be Y. You tell them angles opposite equal sides. And then you tell them angle P1 must be angle T2, must be equal to T2, must be equal to Z. Same reason. I so wish we could say, if we said only one, you just tell them look above, but hey, we need to write them, eh? And then T1, right, angle T1 will be equal to angle S1, which both of them are going to be W, angles opposite equal sides. Just that for this theorem, you see that we have added we have added another block. In other theorems, remember, we had only 3. So now we just added another one. Because it's a quad, you are working with 4. Okay. So after doing that, where do you go to? Or rather, what do you then say, right? Remember, you need to prove that angle P plus angle S is equal to 180 degrees. So good people, you see, for this theorem, you don't have to worry yourself that much, okay? You have to think of it as if you were working with theorem number 1, the one we first proved. Remember this one? Whereby you look for the expression of O1. Ne? So for this one, that is what you are also going to do. You're going to look for the expression for O1. Ne? So you're going to say angle O1 in this triangle. Angle O1 is in this triangle. Angle O1, right, plus angle P1 plus angle T2, they must give you 180 degrees. Okay, they must give you what? 180 degrees. Why? You tell them this is because this is sum of angles in a triangle. Right, so that means angle O1 should be equal to 180 degrees minus 2Z. You don't even have to substitute here. We just tell them O1 is, because we already have it though, by the way. Just that today, or rather now, I did not write it. This is 180 minus 2Z. This is 180 minus 2Y. This is 180 minus 2X. This is 180 minus what? 2W. By the way, after getting that O1 is equal to this, you know what you're going to say? You're going to speak a bit of English. So you're going to tell them similarly. Similarly, angle O2 will be 180 minus 2Y. And then angle O3 is going to be 180 minus 2X. And then angle what? Where am I leaving? I'm leaving angle O4. It's going to be 180 minus 2W. Right, that's what you tell them. Then for the finishing move, because there are always 2 finishing moves there. Remember, for this one, we started with this part, and then the finishing move. These were the 2 finishing moves. And then for this one, it was getting O1, and then those were the 2 finishing moves. Apart from this part, that is always the same for all of them. So even here, this is the first move, and then the other last finishing move is to then do this. Because you have O1, O2, O3, O4, and you have 4 of them, I need you to remember that you're going to say angle O1 plus angle O2. You're going to add all of them. That is why you were getting them in the first place. So you're going to say O1, O2 plus O3 plus O4. You're going to tell them that it must be equal to 360. Why? You just tell them revolution. Because all angles around a point, they add up to 360 degrees. So that is just the revolution. So that means what? That means O1, which is 180 degrees minus 2z, plus O2, which is 180 degrees minus 2y, plus O3, which is 180 degrees minus 2x. Okay, please also allow me to just move this a bit. Can I make it smaller? Let me check. Oh, wow. Yasmara technology is one beautiful thing. Let me take this here. Right. It's still there though. It's still there. So we have 180 minus 2x, and then O4. Where is O4? We said it's 180 minus 2w. 180 degrees minus 2w is equal to 360 degrees. Good people, it's simply saying 180 minus 2x, 180 minus 2y, 180 minus 2z, 180 minus 2w. You must just have z, y, x, w, and you are good. And on others, you just had 2x, 2y, 2z. This time you have what? 2x, 2y, 2z, 2w, but you're just putting 180 minus 180 minus 180 minus. Good. I'm just trying to make sure you see the link to these theorems, all of them. Now, what do you do then? You add 180 plus 180 plus 180 plus 180. I think you should get 720 degrees. And then you're going to have minus 2x minus 2y minus 2z minus 2w is equals to 180 degrees. Oh, 360 degrees. Oopsie. 360 degrees. Then after that, what do? You're going to take all of these with the negative signs. Take them to the other side so that they become positive. We don't like negatives. Then the 360, you're going to take it this side. So it means you're going to have what? 720 degrees minus 360 degrees being equal to 2x plus 2y plus 2z plus 2w. That's good. So what is 720 minus 360? It so happens that it's actually 360. Then you have 2x plus 2y, right, plus 2z plus 2w. Beautiful. That is a very, very nice equation there. Okay, so now what do? Please, I'm going to also ask you guys to allow me to finish this somewhere because I always run out of space. So I'm gonna like finish it that side, or maybe I can continue with it here. So I hope that you will still be able to see that. So what I'm going to do here, good people, is that I'm gonna divide everything by 2. Okay, I'm gonna divide everything by 2. So if I divide everything by 2, meaning 360, so you can write this divided by 2. It will mean that 360 divided by 2 is what? It's 180 degrees. And then 2x divided by 2 is x. And then you're going to have y plus z plus w. What do you know? You have proved the theorem. You are done. How? But how are you done? How are you done? You simply say, remember angle P. Angle P is z plus y. Angle P is what? Z plus y. Check. Z plus y. What is angle S? What is angle S? Right. What is angle S? Angle S is x plus w. Angle S is what? X plus w. So you have actually proved the theorem. So what do you write? You just write simply, therefore, 180 degrees is actually angle P plus angle S. Then you are good. What is the beauty of this one? The beauty of this one now is that you can also say, if they wanted you to prove T and R, you know what you you just say, okay, T and R. Ooh, I'm hoping I have a nice pen. Yeah, this one. T and R is W. Look at T. T is W and Z. Ne? Look at it. W and what? And Z. What about R? It's X and Y. So R would be the remaining X and Y. So we just substitute there. We just tell them that angle T plus angle R is 180. So the theorem, the proof works for any pair that you are asked. That is what I'm just trying to say. The proof works for any pair that you are asked. All you have to do or to remember for me is the routine, of course, but I need you to remember that for cyclic quads, we have to find O1, then find O2, O3, and O4. After that, add those O1, O2, O3, and O4. As simple as that, then you have proved the theorem. Now here's a bit of a disclaimer. I know that there are other ways of proving these theorems that were taught at school, that I personally was also taught. I just happen not to like them. But if you like them, it's not a train smash. Please stick to them, okay? If you like those ones more than these, please stick to those ones. Nah. But I feel like these ones kind of like have the same general trend, so I will always know what to do, unlike the other ones. Yeah, but like I said, right, you choose whichever one you would like to use, right? I just needed to put it as a disclaimer so that you don't say these are the only ways of solving them. Okay, so just to recap, right, so far we have looked at this theorem. Angle at the center is twice the angle at the circumference. And how did we prove it? Remember, it was simply about constructing your Mercedes-Benz triangle there. We've also proved Tan-chord theorem. How did we prove it? Remember, it was all about your Mercedes-Benz triangle. We've also proved this one, which is opposite angles of a cyclic quad. How did we do it? By simply joining and making our 4 triangles, because we were now talking about a cyclic quad. Now for a cyclic quad, remember we added O1, O2, and O3. For this one here, remember we needed to remember the theorem about tan perpendicular to radius to get T1, and thus be able to get J and then equate them. But how did we get J? If we can remember, we added this angle, that angle, and that angle. The angle in the bigger triangle. The angles in the bigger triangle. Same thing here. We got O1, just like this one. We got O1. However, we then added the angles in the bigger triangle. So where you are adding the angles in the bigger triangle is on Tan-chord and angle at the center. You are adding all the angles in the bigger triangle, right? But for this one, which is cyclic quad, we only add the angles around the point. You see, those are the trends that I was talking about. Right, we still have a long way to go. But these other ones, they don't work the same way as these 3 above. Hence, I wanted to show you the first 3 above. So whatever we did for these 3 is very much different from what we are going to do for the last 3. Okay, so please know that. Right, I hope we are still together. Now this is theorem number 4. Okay, theorem number 4 is talking about what? Can I select this and move it? Oh, nice. So theorem number 4 says that the perpendicular line drawn from the center of a circle to a chord bisects the chord. In short, line from center perpendicular to chord. What it says is that if you have a line from the center and then that line is perpendicular to the chord, then it's going to bisect the chord, meaning that it's going to cut the chord into 2 equal parts, which are AB and BC. Okay, so we have to prove this theorem. So what do we need to prove? We actually have to prove that AB is going to be equal to BC due to the presence of a line from the center which is perpendicular to the chord. So we need to prove that indeed that line is going to bisect the chord. We are proving this statement or this phrase here, that the line bisects the chord. Now, as a disclaimer again, I know there is a way or a method of doing this. That method is talking about congruency. I just do not like the method. I just don't like it, good people. I'm sorry for saying it, but I have said it. I don't like the methods. So let me show you my own way of proving this. Right? I like joining things. So I'm going to join A and O. Then I'm going to join O and C. Just that here I'm not going to have my favorite Mercedes-Benz logo, but it's fine. I've joined AO and OC. Then what is next? What must I do? I must label. So I'm going to label this B1 and B2. But there's no need for me to label this A1 because there's no other angle apart from angle A1. So it's just angle A. This one, there's no need of saying C1 because there's no other angle apart from angle C1. So I'll just call it angle C. Good. Then what do? I tell them what I just did. Tell them again. Join OA and OC. After doing that, what are you going to have? Remember that the lines are going to be equal. So you tell the examiner, right, that OA is equal to OC. Then you tell the examiner that this is because those lines are radiuses. So you say radi. Then after that, what do? Just invite our favorite grandpa. Who is our favorite grandpa in mathematics? Anyone who can tell me? Do you remember our favorite grandpa? Who? Mercedes-Benz. Grandpa, as in a person that we love so much in maths. Right? That grandpa, nice, is close to our hearts, good people. Oh, life science students, I know you are there. Okay, it's close to our cerebrum. Pythagoras, perfect. Our favorite grandpa is Grandpa Pythagoras. So what are we going to do? First of all, we're going to tell the examiner that since here it is B1 and it's 90 degrees, angle B1 is going to be equal to angle B2 because when you add them, you get 180. So it can only mean that B1 and B2 should be 90 each. Let's actually write it. So we're gonna say B1 plus B2 is equal to what? 180. This is because B1 and B2, these are angles on a what? On a straight line. So that should mean that B1, remember that, B1 is 90 degrees already, and then here we have B2, and then they equal to 180. So therefore it means angle B2 should be equal to what? 90 degrees, right? So we know that this is also what? 90. Now after doing that, why are we making sure that we have both 90 degrees? This is because our grandpa said to us his theorem only works on right angled triangles, unfortunately. Okay, around there or one. So we're going to work with the first triangle first. So you're gonna say OA squared, right? Try to use the same wording you use there. So you're gonna say OA squared, since it's the hypotenuse, the side opposite the 90 degrees, right? OA squared is going to be equal to what? OB, right? OB squared plus what? AB squared. Why? This is because of our grandpa, right? Pythagoras theorem. Perfect. You said that about OA squared. Same thing can be said about OC. So you say OC squared is equals to OB squared. This line again, OB squared plus what? Plus BC squared. This is because of our grandpa Pythagoras theorem. Perfect. Now wait a minute. I'm gonna write it here to say, but OA is equal to OC, right? OA and OC are equal, is one thing. And OB is equal to OB, meaning that OB is common. It's also OB and OB. If this and that are equal, and then this and that are also equal, that can only mean, right? That can only mean that AB squared is equal to what? To BC squared. Taking the root both sides, what are we going to have, good people? AB is equal to BC. You have proved the theorem. Good shot. Good shot. But why am I saying AB squared and BC squared are equal? Well, if you want to maybe try and see if what we're saying to you is true, it's always good to verify. So what you can do is that here you can make AB squared the subject of the formula. That will be AB squared is equal to OA squared minus OB squared. And in this side you make BC squared the subject. That is going to be OC squared minus what? Minus OB squared. Now since this and that is the same thing, and then this and that is the same thing, then therefore these two should be equal. Then you take the root both sides. AB is equal to BC. You have proved the theorem. This one is very, very fast. I like it a lot. If you are given this one, you should smile. You have one. So how does it work? Remember, you're just joining OA and OC. You tell them that they are equal because it's radii. Then after that, you say to them, B2 also is 90 degrees because you only gave me 190 degrees. They're only going to give you one, by the way. So you have to prove that the other one is also 90 degrees. Then you can invite our grandpa, his theorems. You tell them about the theorems of grandpa. And then you also say, but we already said OA and OC are equal. And OB is common. Then that means AB squared is equal to BC squared. Quite simple, right? So that is the theorem there. So whenever you're using the theorem, you're going to tell them line from center perpendicular to chord. Right. Remember, if you have any question, you can buzz, you can just tell me, right? In most cases, I'm not able to see that side, like who's raising their hand. So please just tell me. Good. Then we come to this guy here. We come here. This is grade 12 now. Grade 12. And you know, grade 12, this theorem, most people, they solve it, they don't understand why they are doing it. Some people, they have crammed it. And then some people just try their best to cram it. You might be falling from there. Then there are people who actually genuinely understand it and why are we doing some things. But worry not, right? We are going to talk about it so that whenever you are proving it, you always remember what you are doing. For us to understand it though, let me do this, right? Perfect. Let me do this. Let's talk a bit about a topic that I know we've been doing a lot of times. Let's talk about the areas of triangles. Right. Let's actually first start talking about the areas of triangles. Now, if I have, so let me have some triangles here. Right. Da-da-da. This is the first triangle there. This is the second triangle there. And then perfect. I told you technology is beautiful, guys. And then let's say another one here. Where can I draw it? Let me draw it here. I'm hoping it's gonna realize and see. Perfect. So this is what we have, right? Good. Yeah, those are nice triangles. I didn't think I'd get them correct, but yeah, here we are in life. So this is A, B, and then C. How can I get the area of triangle ABC? Who can tell me what is the area of triangle ABC? Oh, by the way, please always get used to writing area triangle, area triangle, area triangle, because you're going to do that a lot. Good people, a lot. So if you can already practice your handwriting area triangle, you'll be okay. Because there are some instances whereby we just forget to write area, or we just forget to write that triangle there. So please, area triangle, you already get used to it. Okay, how do we get the area of triangle ABC? Anyone real quick? So the area of triangle ABC, right? The area of triangle ABC, generally the area of a triangle, area of a triangle is half the base times the height. Let me try to move this a bit, this side. Good. So this is the general formula for the area. So all you have to do is, you have only two tasks. You must just identify the base and identify the height, and then your life is perfect. If you're able to identify the base and the height, you're okay. But this height, let's understand that this height is actually called the perpendicular height, right? The perpendicular height, meaning that this height must always be perpendicular to the base. If this is your base here, if this is the base, the height must always be perpendicular to the base. If this is your base here, the height must always be perpendicular to the base. Let's understand that. Okay, so let's check here. We can take our BC as the base. That is why people get it wrong here. People think that we actually have a base of a triangle. Good people, we don't have a base of a triangle. A base is only a base if it is perpendicular to the height. I spoke English. Let me try to break it down. Why wouldn't you call BC if you don't have a perpendicular height? Why wouldn't you call it a base? Look at AC, right? AC can be my base, but what makes it a base? It's because I would have a perpendicular height here. That's why I would call AC my base. So it means if I don't have a perpendicular height on AC, AC cannot be my base. As simple as that. BC can only be the base if you have a what? If you have a perpendicular height. Okay, so if I have my perpendicular height on BC, I cannot call AB the base. I cannot call AC the base. The base is going to be the one that is perpendicular to the height. I know you get me. So I'm going to write this as H. Right, so the area here is going to be what? Half of the base. The base is going to be BC times the height, which is the one we constructed. Good. If I happen to have another height in the same triangle, right? If I happen to have another height here that I can draw, right? And then it's perpendicular to AC, then that height, I call it K. What is another way I can now use to calculate the area of triangle ABC? I can now say the area of triangle ABC is going to be half, which will be my base now. My base will be AC. Why? Because I have a perpendicular height K. Okay, so it means there are two ways of calculating the area of this triangle. I can either say the base is BC, provided I'm talking about this height, or I can say the base is AC, provided I'm talking about that height. Okay, so the base depends on which one is the height. I know you get me, I know. So let's have another one here. Let's call it triangle KFC. Now I'm becoming hungry. But then let's call it triangle KFC. And then let's make it a right-angled triangle. What is the area of triangle KFC? Right? the area of triangle KFC will be half. Which one is the base? I will call FC my base. Why? Because the height is KF. The base is perpendicular to the height. Okay, so that is why for this triangle, you don't have to construct the height, because the height is already a line that will be perpendicular to your base. Would it be correct for me to say the area of triangle KFC is half BC? Oh, no, sorry. Is half KC times FC. Would it be correct? If I am saying KC is my base, KC, is it true that FC is the perpendicular height? FC is not perpendicular to KC, so this is very much wrong. But it is correct for me to say, in fact, let me ask, is it correct for me to say the area of triangle KFC is going to be half of KF times FC? Right. Anyone who can tell me whether it's correct there? Is it correct?
Yes.
It's correct, yes. Because why? KF?
K
Mm-hmm.
perpendicular to C.
Aha, KF is perpendicular to FC. So that is why it's correct. So I can calculate the area of triangle KFC using this or that. Not this one. Beautiful. Then we have some angles, right? We call them obtuse angled triangle. Let me call this DEF. These are obtuse angled triangles. And now, why do we call them obtuse? Because an obtuse angle is an angle bigger than 90 degrees, but less than, say, 270. So here, less than 180. Yeah. So this is an obtuse angle triangle. How would we calculate the area of this triangle? Area of triangle DEF.
Construction.
Construction. Why do we need to construct, sir?
Because we cannot have a perpendicular line in the triangle, so we have to draw a perpendicular line from D to F. Construction.
Oh, so I need to have a perpendicular line from D to F. Let me do what you just told me, sir. I just have this.
But like that, we have a straight perpendicular line.
No, man, I'm just messing with you. Okay, that's very correct. We do need a perpendicular height. In this case, it would be very wrong of us to say half EF and then we say times DF, because EF and DF are not perpendicular to each other. So we actually need to construct a what? A height. So here we can call it height H that we have constructed. It is perpendicular to the base, you see. So we do have half EH times H. So we have an external, it's like an external height, but your base remains as EF. Your base is EF. It's not E until here. This is not the base here, right? Don't call it the base. It's not. The base is E to F because the triangle is DEF. Okay? I hope that is clear. So, thank you so much for that, sir. We do need to construct a what? A height, a perpendicular height. Great. Let's have another one here, which we'll call COB, right? So we need to get, it's also an obtuse angle triangle. So if we were to get the area of this triangle here, right, area of triangle COB, right, we would say half. What would be our base there? OB, right? So OB must be the base there, good people. But OB is only a base if you construct a perpendicular height from C down here, right? So if you construct this perpendicular height, yes, this one would extend like this, right? So that is why we're constructing our perpendicular height there, right? But our base remains as OB or BO, right? And then our height would be the one we just created. So hence we just call it K. Right. So if you understand these, good people, then you know how to calculate the area of a triangle.
Sir,
Mm-hmm.
sir, where can we apply the area rule?
Oh, when we want to, the area rule is applied on any triangle. It's a formula to get the area of any triangle. However, if you can remember, the area rule says that the area of a triangle is equal to half AB sine theta, ne? So AB are the length of the two sides, ne? This would be A, this would be B. Theta is the angle in the middle, okay? It's the angle in the middle. So for this triangle here, if I wanted to get its area, I can use the sine rule by saying that BC times what? I would say half BC times OB, and then I say sine of what? Of the obtuse angle, which I can call angle B. But the problem is that in most cases here we are not going to have the angle. We are not going to have the angle. So to get the area, you would have to use these traditional methods. But that is a very good observation there. A very good one. Okay, so I hope that we're okay there in terms of calculating the areas of triangles. Now, before we dive deep into the theorem, can someone tell me, right, what are parallel lines? Can someone define for me what are parallel lines? I will buy them 10 rand airtime if they can describe to me what are parallel lines.
Lines that don't meet.
I know you know that one from your teachers out there, whoever taught you, but I don't want that definition, because that one, I just don't like it, good people. Give me a beautiful definition.
Yeah.
Mm-hmm.
The opposite line or parallel lines or lines that are opposite. It's the same gradient, but never meet.
I see what you did there, Mr. Liema. I see it. Right. You going to trick there. You want to trick me. No, I still don't like that definition. I want a beautiful definition, good people. Can someone tell me what are parallel lines? 10 rands airtime. Going once?
Straight lines that are parallel.
Or straight lines that are parallel. Yo. And I'm asking about parallel lines. You're still using parallel. Hey, man. Okay, but at least you tried, guys. I'll give you that, eh? But I get to keep my 10 rands airtime. That is perfect. So, parallel lines, good people. These are lines, right, that are equidistant from each other, right? These are lines that have the same distance between them. That is what we call parallel lines. Are lines that have the same distance between them. Meaning, on any part between those two parallel lines, the distance is going to be the same. So if you measure this distance here, right, and then you measure the other one, they're going to be the same. I know for me here, I didn't draw it quite nicely, yeah? Don't I have a ruler here? Oh, I don't have. Do I have? I don't have. Okay, it's fine. but these are lines that have the same distance between them, good people, right? That one of lines that never meet, it's okay for a grade 10 learner. I will give them marks, but for you guys, you must know this one, okay? There are lines that have the same distance between them, right? And why is it important to know the definition? Let's draw two parallel lines. I'm not sure I'm gonna be able to draw them exactly being parallel. Is there anything that can help me here? Unfortunately, there is not anything that can assist. Okay, it's fine. So these are the two parallel lines that we have, right? Now, since these are parallel lines, I'm gonna put some triangles in there, okay? I'm gonna put some triangles. Let me have this one here, and then have this. Great. And then let me have this one here, and then let me have this. Unable to recognize. How? But it was visible, this one. Yeah. Hila. Perfect. Those are my two triangles. Now I'm gonna call them, right? Please note that here it's a point and a point, right? So let's call this one A, B, and then C, right? Then let's call this other triangle AC. Let's say ACK. Okay. Now, please assist me, guys. Let's calculate the area of triangle ABC. The area of triangle ABC. Remember, it's going to be half of the base. The base is going to be what? AC, right? And then, remember, it's an obtuse angle triangle. So we do need to construct a height. So I'm quickly going to construct a height here. Here is going to be the height. A nice perpendicular height. A nice perpendicular height. So this is going to be H, right? So you say times H. And then let's talk about the area of triangle AKC, right? AKC. That will be half of the base. The base is still gonna be AC. Now I'm looking at this one. If I can, this thing can't highlight. It can't paint. Okay, sorry. So it means I'm gonna have this, have that, and then have myself that. That is a triangle I'm looking at, KAC. Okay. So the base of that triangle is also going to be AC. However, the height now, I also have to construct a perpendicular height here, of which that height we're going to call it what? K. Perfect, we're going to call it K. And then, so it will mean that times K. But good people, let's remember that these are parallel. These triangles are between parallel lines, right? So that means actually K is equals to H. Why? Because these are between parallel lines. These triangles are between parallel lines. So this height here is gonna be the same as the height there, because parallel lines have the same distance between them. Therefore, this actually means that the area of triangle AKC is equal to the area of triangle what? ABC. Good. Because H and K are the same. Why are we saying this? This is because of this reason. Number one, these triangles, they have the same base. We can see that the base is AC, the other one is also AC. Number two, these triangles have the same height. Why do they have the same height? This is because they are between parallel lines. They are between parallel lines, so they have the same height. So if triangles have the same base and the same height, that means their areas must also be the same. So the area of triangle ABC right? Meaning the whole area here is going to be equal to the whole area here. Okay, because those triangles have the same base, same height, they are between parallel lines. Right, I hope that we understood that. Let's now go to this theorem, right? Everything we said was building up to this theorem. So on this theorem, when you prove it, what do? They are going to say to you, prove the following. They will say, prove that AD over DB is equal to AE over EC. Whenever you get these, good people, I want you to remember the following, or what you're going to do. If you have ever watched the movie of X-Men, I used to watch this when I was young, X-Men, then you would be very excited whenever you see this triangle. So still, you're going to do what? You are going to draw for me there X-Men. You're going to draw X, right? You're going to say you join B and E, then you join what? C and D. So you have yourself X there. Sorry. After that, after you have joined them, what do? You then, so you're going to tell the examiner, okay, to say, number one, join B and E, meaning join BE and what? And DC. You tell the examiner that. But then you are now going to do something that is very different from the other theorems we've been proving. Now you're going to do a bit of construction, right? So you're going to say construct. You're going to construct what? You're going to construct two heights, height H and height K. And I'm going to explain why do you have to construct those heights. So the heights are going to be constructed here. So here you're going to construct your two heights. Remember, they must be perpendicular heights. Why are we constructing the heights, by the way? Remember, triangle ABE, for me to calculate its area, I must have what? I must have a base. And I can only have a base if I have a perpendicular height. So for me to have a perpendicular height, that is why I'm constructing it to say I must have the first perpendicular height here, and then I must have the second perpendicular height here. Why are we not constructing just a perpendicular height here? Well, it's because of the nature of this theorem, of where we are going. These constructing them on those two sides is actually going to assist us, because we will be killing two stones with one bait. Okay, so here we say height H, we're gonna call this height H, and then this one we are going to call it height K. So good people, height K, I'm gonna give it a nice pinkish color. Height H, I'm gonna give it a nice orangish color. Ooh, English, yeah, orangish color there for H. Right, then you're going to do this for me. You know, as maths people, good people, we are mostly lazy. Well, I know that I'm usually lazy, so this is what I do, right? Do you see that here it's written AD? You are going to say for me area of triangle AD. But a triangle needs three sides. So since I already said AD, I'm going to say ADE, right? We are always going to work with this triangle on top, this one, over the other triangles I'm going to show you. So we're always going to say area of triangle ADE, the one on top, over something, yeah, over something here. And then I'm going to write the same thing again, area of triangle ADE over something. Now what is that something? Well, below here you're going to write area of triangle. Do you see here? What do you see here, good people? DB. It's at the bottom again, DB. You are going to write exactly the same thing, DB. DB. Actually it is this one, DB. But you need to make it a triangle, right? So can I say DBC or can I say DBE? Well, you are always going to work with these two triangles. Now let me paint them. You're going to work with this one, BD. Yeah, you're going to work with this one, and then you are going to work with this one here. This one here. Hoping I trace it nicely. The ones on top there, good people, those are the ones you're going to work with. So it's like a gene. If I wanted to draw a gene, I can't draw it, but when I draw a gene, I usually draw it like this. Now, that's a nice gene. So these are the triangles we're going to work with. You see, they look like a gene, like, you know, boys wear skin jeans, right? So, you know, something like that. So those are the two triangles we're going to be working with. So that is why I say DB, DB, and then I just say E. Okay, DBE. On the one at the bottom, I'm still going to say area again, and I say triangle. You see what is happening here? It's EC, ne? So I'm gonna write EC, and then I'm going to have D, right? To say ECD. Perfect. First step done. Now the next thing is to say, now the triangle ADE, its area, it's going to be half of, which one is the base? Can I say the base is DE? No, I can either say the base is AD or AE, because the heights are there, the perpendicular heights are there. You must show that they are perpendicular. So because here I have AD, I'm gonna say half of AD. You're just copying from what is given in the question, and then the height is H. Down here you're gonna have what? Half of this. Okay, so we're almost there, good people. Let me try to remind you what we did to get this far. We said we're going to join BE and DC. This is D here. BE and DC. Then after that we construct height H and height K. Why? Because we need to have heights for us to be able to calculate the area. So for the area of triangle, you see there's AD, so we say triangle ADE, right? We say it's going to be half AD, because there's AD on top, times the height, which is height H that we constructed. But now we needed to get the area of triangle DBE. Good people, check. The area of triangle DBE is actually an obtuse angled triangle. Now, what you don't usually do in the exam that I'm going to advise you to do is the following. I know you don't usually do it. If you do, you can tell me, but I usually do this. But I know you don't, Shane. Let me see. I usually do this, and then obviously you are going to rotate your page. Me, I'm going to rotate this because technology said I can. Right, so you can see I'm rotating it, right? Oh, it doesn't want to be steady. Oh, and then let me do this, ne? Before I can rotate it, let me remove this part, take it a bit down. Good. Right. Sorry guys, let's take it down a bit first, right, before we can do the nice things. So here I am, look at, ooh, hi, we tried him. Yeah, here it is. Look at it, guys. Look at the obtuse angle triangle. You see it? Hey, let me take you back here. Doesn't it look like this one here that we had? This one. Look at this one, and then I want you to look at this one here, BDE or DBE. You see the pink one, this one. It's exactly the same as what we had there, right? And we needed a height for us to calculate the area. Where is the height? Look at it. Height h, the perpendicular height h is actually going to be the height we're going to be using. Okay, so we then say the area there is going to be what? dB. Remember, the base is going to be dB, right? All guided by dB here, and then times the height is going to be what? The height is going to be h. Right, then what is going to happen there? H and H will cancel, then you'll be left with AD over what? Over dB. Right, then we are done with this part. Let's go to this one. Again, I'm going to rotate. Oh my, nice. Let me rotate this one. Look guys, you see magic. Nice. Aha. Now I'm going to be looking at triangle ADE from this point of view to say now the base is going to be AE and the height is going to be K. So I'm going to say half, and then the base is going to be AE times what? The height is going to be K. I know they are not nicely drawn just because I drew the height somehow, but it's actually a height. Over half. Now look at this one here, EC, right? In terms of the orange triangle, it's also an obtuse angled triangle. So the base is going to be EC, right? And then the height is going to be what? It's also going to be K. So what does that mean? That means that AE will simply be equal to, will be over EC, because half and half, they cancel, K and K cancel, this and that cancel, that and that cancel. So usually just tell them here that this is because these things actually have the same height. That is why we ended up having that thing. So even here, you just tell them that those things, they have the same height. If you can check those triangles, this one on top and the one at the bottom, they actually have the same heights. Okay, then let me take it back to how you are used to seeing it. Thank you. By simply doing what? I rotate. How do I rotate it now, guys? It's not allowing me now. Why? Oh, here it is. So now we take it back to how you know it, right? Yeah, this is how we know it. But we saw everything, right? The pink one has the height h, and then ADE also have height h. And then the orange one has height k, and then ADE also have height k in terms of that part. Perfect. So because of this, right, we have AD over DB, AE over EC. But that is not enough to tell us that AD over DB is equal to AE over EC. We need one last move, nice finishing move, to actually convince the examiner that for real, those things, man, they are equal, right? So what do? I want you to shift your focus to the bottom part, right? I want you to focus here on these ones at the bottom. Nay, look at those areas, good people. Look at them here. Look at BDE, ne? Here it is, here, BDE. And then look at DEC. It is this one here. Beautiful. Let's remember that DE is parallel to BC. Good. Tell me something. If I were to extend this line here, the parallel line, and then extend it also this side, that parallel line. Ooh, yeah, extend it that side. Do we agree that if I were to calculate the area of triangle DEC, I would say the base is DE, and then I would have to have a height here constructed, a perpendicular height. Same thing for this one, I would have to have a height here constructed, and that height would be the perpendicular height. And then I could call it anything, H maybe, and then K. But do we remember that because they are between parallel lines, those heights are going to be the same? And look at the pink triangle and the orange triangle, they share the same base. And now we are saying because they are between parallel lines, they have the same height. So what does that tell us about these two areas here? That means the area of triangle DBE is actually equal to the area of triangle ECD. Why? Because those two triangles, they have the same base, number one. Number two, they have the same heights. Why are we saying they have the same heights? This is because they are between parallel lines. Right. So if this and that are equal, and this one and that is the same thing, so that means therefore the area of triangle ADE over the area of triangle DBE will be equal to the area of triangle ADE over the area of triangle ECD. And then therefore that will mean that AD over DB is equal to AE over EC. Then you have proved it. So this theorem, the proof has a lot of things that are not said, that are not told by our teachers or our textbooks. But I hope that you can see, guys. You see this gene there? It is almost exactly the same as what we had here. If I can flip it, check it. If I can flip this one, don't worry, we can. This is technology. Here we are. Isn't this exactly the same thing as this part? You see, they are exactly what? Exactly the same. So that is why we are saying those two triangles, they must have the same areas because they have the same base and same height. Okay, so that's exactly what we have for those two. That is why we're saying those two areas are equal. And then that's why AD over DB is equal to AE over EC. Beautiful. And then when you use that theorem, please remember to just say line parallel to one side of a triangle. The more we do them, the more you do them in practice. Please do this for me. Every day before you sleep, make sure that you prove one of the theorems. Every day before you sleep, prove one of the theorems. Especially that one that gives you a hard time. Prove it every day. No, like today you prove this one, tomorrow you prove the other one. And don't cheat yourself. Just say today randomly I'm gonna prove this one that I forgot. So that you see whether you remember or not. Good. Then good people, the last one would be this one, right? And then how do we prove this one, right? This one is saying that the corresponding sides of triangles that are similar are in the same proportion. This one already, the case, good people, my English is not coming out. I don't understand why. This one always carries around 7 marks or 6 marks. Okay, and how do we prove it? We're going to prove it using 2 steps, or rather 2 parts, right? So the proof is going to consist of 2 parts. It's going to consist of the congruency part. I know I said I don't like congruency, but it always haunts me. So the congruency part and the corresponding angles part, right? And the corresponding angles part. In terms of what we need to prove, right? We need to prove, right? They're going to say that prove a theorem that says that kf, no, mn over kf is equal to mo or mo over kc. They usually take one of them, but actually when you complete it, it's also consisting of on over fc. So this is what you are required to prove. Right. Brace yourself. Be mentally prepared for this one. How do we prove that lines are congruent? Let's maybe start there. Triangles are congruent. Remember that if I can have a triangle here, right, I'm just gonna call it A, B, and C. Ne? So I will say that on triangle ABC, this is 2 units, 4 units, and then this is 30 degrees. And then I have another triangle here, which is EDF. It so happens that here is 30 degrees, and then this line is 4. It's 2 units, and then this one is 4. Can I prove that these two triangles are congruent? Yes, we can. How? We can say in triangle ABC and triangle EDF, ne? In those two triangles, we can see that AC is equal to what? AC is equal to DF, right? In this case, it's given. AB is equal to EF. It's also very much given. It's visible from the diagram. And then angle A is equal to angle F, right? Both are equal to 30 degrees. It's also given. So because of this, alright, right, we can then say, therefore, triangle ABC is congruent to triangle EDF. Okay, this is what we conclude to say. Those triangles are congruent, and your reason is going to be side, angle, side. Remember, there are 4 conditions for congruence, but for today, what we're going to focus on is this one only: side, angle, side. It's what we need for this one. Good. I hope we have reminded ourselves of how to prove that triangles are congruent. We just have to prove that the sides are equal, and then the angle in between them. By the way, it's not called side, angle, side. It's called side, angle, side for a reason. We don't actually say side, side, angle, or angle, side, side. No, we don't really say that. We say side, angle, side. This is because usually that angle must be the included angle, meaning it must be the angle between the sides that are equal. Okay, so we usually call it an included angle. An included angle. Oh, if you still remember where your hands are, right? If you can look at them, they are like this, right? 1, 2, 3, 4, 5. Our hands are more or less like this, right? I tried, guys, I'm sorry. Sorry, guys. Okay, so these are our hands, right? And these hands, right, when you look at if you can take 2 fingers, right, and do this, right, okay, so this one, it means you would be folding it. Let me check my hands. Oh, even this one, you'll be folding this one, you'll be folding this one again, and then this one you'll be taking it up, and then the other one will also be like this, and then you fold the other ones, and then fold the other ones. Good. So it means you are saying 2. Do you see that? I know girls pose like this when they are taking a pic, right? They will be saying, I don't know what's the 2 for, right? I'm not even sure till this day why do they say 2, but then this is what you usually do. Ladies, you can confess that it's true. I know. Whenever you're doing that next time, I need you to remember that this is a side, and then this is a side, and then in between you have the included angle. So I know that you were actually telling us boys that I've proved congruency, just that you don't want to say it, right? So we understand that it's a code. I'm sorry to tell it to the boys, right? Yeah. Am I not saying the truth, Miss Clady? Is that not true?
But we don't have 6 fingers.
6. 1, 2, 3. How did I make them 6? Ask kids. Okay. Okay. Let me do this. Don't worry, guys. I got you. So that is just 1. The thumb there. Right. Oh, it's a thumb. It's 1 finger. Hey, 1. It's 1 and then 2, and then you have your 2 there. You're posing, and then you're saying, I've just proved congruency. The side and the included angle are equal. So it means you've proved congruency. Right. So I hope you remember to prove congruency. Where I'm actually going, right, is to prove this theorem, this long theorem. So the congruency part, I hope we have covered. And then corresponding angles, I think that one we can remember from grade 9, that if I have a set of parallel lines and then I draw a line crossing the 2 parallel lines, I form an angle here, and then I'm also forming an angle here, and those angles are equal because those are your corresponding angles. Or we can have them like this. You can say I'm forming an angle here and then I'm forming an angle there. We usually said these are F angles, meaning maths is fun, right? Maths is fun. So those will be your angles there. And then if you have parallel lines, remember these two, when you add them, is coincident angles add up to 180. And then remember the alternating angles, of which alternating here would be this angle and that angle. Or you can say this angle and that angle there, which makes sense. If this angle and that are equal, that is why this and that should also be equal. You know, it kind of like makes sense. So that is what we have there for corresponding angles. It's just something you need to remember. Trust me, guys, if you can remember those things, corresponding angles and congruence, you are done with this theorem. So we are going to prove it. But when we prove it, good people, I need you to remember this English that we are going to tell the examiner. So you are going to say, first of all, this theorem says a lot of words, but it's fine. First of all, you're going to tell the examiner, please start by doing this. You tell them, this is the construction part, right? Construction part. You're going to say, please, examiner, mark off, right? Mark off any letter you want. If your name is Vanessa, I know you'll use V. I know Vanessa will use V. So tell them, mark off V such that MV is equal to FK. So that when you mark off that, now marking off, usually we use what? We use a cross. So this is marking off. When you mark off V here, it should be equal to what? That should be equal to FC. KF. You're just going to try, and it's more of like putting this triangle. You see this triangle? It's more of like taking this triangle and putting it here. Putting it here. That's what you just want. That is why this side and that must be equal. It means that M, whatever we're gonna have, must be equal to KC. Okay? So it means here you are also going to say mark off, right? Mark off. If you're Miss Clady, I know you're gonna use T, right? Oh, by the way, you must include where you are marking off, ne? So mark off V on MN, right? Mark off V on MN to say draw a mark of V on MN such that that MV will be equal to KF. And then mark of T where? On MO, right? So mark of T on what? On MO, such that MT will be equal to KC, such that this one will be equal to that one. Like I said, it's just taking this triangle and putting it here. Then what are you going to say after that? You are then going to tell them join now. You're going to join what? Join VT, the ones that you have there. So you're going to say now join VT. So we can have a dotted line there. Beautiful. But join that VT, ne? such that the VT you have is parallel to ON. Okay, such that the VT that you have is parallel to ON. Good, that's what you're going to tell them. It's a lot of English, but I know we can remember it. Mark of V on MN such that MV is equal to KC. Mark of T on MO such that MT is equal to KC. Right, like I said, it's just simply taking this triangle and putting it here. Right, and then now, right, remember, ne, we are proving that similar triangles have the sides in the same proportion. This means these two triangles are already similar. What does similar mean? It means that the triangles have the same angles. You understand me? So that tells you that angle F is going to be equal to angle N, angle C is going to be equal to angle O, okay, and then angle K is going to be equal to angle M. They are not necessarily all of them equal, like F is not necessarily equal to C equal to K, but we're saying the corresponding angles, meaning F and N are equal, C and C are equal, K and M are equal, because these are what? These are similar triangles. So you're already dealing with similar triangles. You are trying to prove that the sides of those similar triangles are in the same proportion. So let's remember, mark of V on MN such that MV is equal to KF, and mark of T on MO such that MT is equal to KC, and then join VT such that that VT is parallel to NO. Good. So now, after doing that, what are you going to do? Now, this is the congruency part. Let me write it in pink because it's for the girls. So we say congruency part. When you are proving the congruency part there, you are now going to say in triangle KFC ne, and triangle MVT, right? MVT, meaning the newly formed triangle. You say now KF, you're just going to repeat the statements you said above. KF is equal to MV. Then you're going to tell them why by construction, because you constructed it that way. And then you're going to tell them KC ne, is equal to MT. Why? By construction. By construction. And then what are you going to say? Remember now, girls, you have two sides now, right? Now you need the angle in between. So you say what? Angle K should be equal to angle M, right? Angle K should be equal to angle M. Remember, this is because of the fact that the triangles are similar, right? So you will tell them it's because, and they are all, in most cases they are going to give you, né? So this one is actually going to be given. So they are going to tell you that angle K is equal to angle M. That's a nice part of it. Then because of this,
so what if you write common?
common. Common also works. Because the triangles are similar. Yeah, you can also say common because those triangles are similar. Yeah, right. And then now that we have this, now what can we say? We say therefore this means that triangle KFC is congruent. Remember the symbol for congruent, right? Is congruent to triangle MVT. And then what is our reason? Remember, side, angle, side. Good. We have proved that these triangles are congruent. But what does congruency mean? Remember, it means that the triangles are equal in all respects, which means that this triangle is exactly the same as this triangle. The angles are equal, the sides are equal, all of them. That is what congruency means. So that will mean what? That means that that will tell you that it means that this angle here, right? So we say therefore angle M, okay, say MVT, right? Angle MVT is going to be equal to what? To angle F. Okay? Why? This is from congruency. This is from congruency. Now when I'm writing this the wrong symbol. From congruency, use three lines. Okay, that is from congruency. Right. But if this angle and that are equal, you tell them, but angle F is equal to angle N, isn't it? Remember, we already said angle F was equal to angle N, right? And where do we get that? Angle F is equal to angle N. Why? Can someone remind us? Why do we say angle F is equal to angle N? Remember, the triangles are similar. Okay, so you can write that this is because the triangles are what? Are similar. And that's if they did not give you though. So you can say, yeah. Yes?
That's right, yeah.
From, I mostly prefer to just use the fact that it's from similarity. Okay? So I would advise that, right? You must back your statements by the fact that those triangles are similar, because you can't prove these things if the triangles are not really similar. Okay, so it's from similarity. When I say from similarity, I use the three lines facing up. When I'm saying from congruency, the lines are not are horizontal. Then if, since MVT is equal to angle F, and angle F again is equal to angle N, that will mean that therefore that angle MVT, right, should be equal to angle N. Okay, should be equal to angle N. I know, you see this part, that is where we don't like it the most. I personally also don't like it the most there. It's talking about a lot of angles, but please just remember to do this if you want to get it correct. Remember to start by saying, I'm going to give you a nice roadmap to always remember. You're going to say this is equal to that. Okay, that's where you're going to start. Then you're going to say, but this again is also equal to this. Then your conclusion will now be to say, therefore that should mean that this is equal to that. You understand me? Right? Let's start it again. This is equal to this. And again, why? Because of congruency. So I'm going to say this because of congruency. But then this is also equal to this. Why? Because of similarity. Here is congruency, and then here is what? Similarity. Now you can see that the line is horizontal on top, right? So it means these ones must be like this. And then when it starts getting slanted, ooh, why is it do? Okay, let me remove these ones. Oh, my PC is tired now. You can see it's misbehaving, eh? Hi. Okay, so the top part is going to be this, and then this one is going to be like this. Okay, so here it's from similarity, and then the top part is from congruency. Then you then say, therefore this and that is going to be equal. That is this part here. Good, I hope you got it. And then after that, you just needed to prove that. Now that you have proved that this is equal to that, this means that therefore, right, VT, oh my goodness, oh my goodness, okay, it's fine. VT is parallel to ON. Actually, we were going here. Why did I say it? Oh, that's very clumsy of me. Okay, guys, please, this one you just join VT. Nah? Do not put as such that they are parallel, right? Because if you do that, you are going to niche yourself some marks. Some marks are going to go because of that. So, right. So here, please don't put that such that they are parallel. Just say join VT. Nah? So sorry for that. But then here it's where our corresponding angles are equal, so we actually conclude, right? That's when we conclude to say that's when you conclude to say these two must be parallel because the corresponding angles are equal. So we say VT must be parallel to ON. Why? Because the corresponding angles are what? Are equal. Or one. So if corresponding angles are equal, it means that the lines should be parallel. Open. Good. Whew. Then you are done now. That's where you simply then say, your last step now is to say, therefore this means, right, that MN, right, therefore this means you have actually created what you call your proportionality theorem, which is this theorem here that we proved before. Remember this theorem, right? This one. You have created it because you have a line that is parallel to one side of the triangle. So there you would simply then say what? You say therefore MN, which is the longer side, né, over the constructed side, which is MV, is going to be equal to MO over the constructed side, which is MT. Okay. Then you then say, since MV, remember MV is equal to KF, and then MT is equal to what? To KC. Then you say, therefore, MN over KF will be equal to MO over KC. So it means you would have proved this one there. You would have proved it, the one that they wanted you to prove. Okay, so nice theorem, just a lot of words. So it has two parts though. You must just remember that the first part is about congruency, right? You have to prove that this triangle you constructed is congruent to the other one. Then after that, remember what we say here. We say this angle is equal to that because of congruency. That one is equal to that because of similarity. Then that should mean that this is equal to that. Then we can say because these green angles here are equal, it means VT must be parallel to ON, because corresponding angles are only equal if the lines are parallel. Then that was your finishing move, because now you can apply the proportionality theorem. So here it's you applying the proportionality theorem. Here it's us applying the proportionality theorem to say MN over mv will be equal to mo over mt, and just substituting the fact that mv is kf and then mt is kc. Good. So those are your theorems, guys. 6 of them. At first I didn't think we'd cover them, but yeah, those are your theorems, guys. 6 of them in terms of applying them, and then you must know how to just prove them, right? So I'm gonna remind you again that when we check this side, right, where we started, the first 3 are proved in a very much similar way, but remember, this one we need Pythagoras, this one we are talking about areas, this one we talk about congruency and corresponding angles in the proportionality theorem. So actually this theorem is usually used to prove that one. Okay, but then that is what we have in terms of those theorems. Now I also wanted to show you how they are asked in your question papers. Here's the first one here, right? If you can check here, what are they saying? A, B, C, and D are points on the circumference of the circle center O. Prove the theorem which states that angle A plus angle C is equal to 180. So when you get this, I'm just gonna remind you that you remember, you join here, you join there, you join here, and then you join there. Then remember that you're gonna have to label them, isn't it? You label them there, you label them 1 2 1 2 1 2 1 2, and then you have x x y y z z w w, 1 2 3 4, right? And remember, for this one, because it's 4 sides, you are going to add 01, 02, 03, and 04 on your last step. Okay, 01, 02, 03, and 04. It means you must get 01 first, then you get 02, 03, and 04, then you add them. Right. Next, they give you this one. You have to prove, they say in triangle ABC below, M is a point on AB and N is a point on AC, such that MN is parallel to BC. Prove the theorem which states that AM over MB is equal to AN over NC. What do? Join, right? Remember, you're going to join what? This one, B and N. It's white. Yeah, you're going to join B and N, then you're going to join what? You're going to join C and M. Then what do? You're going to construct your height here, and then you construct your height there. Then you remember, you're going to say the area of triangle AMN over the area of, I said AMN because it's AM here. Then I say the area of triangle, remember, MB. So I already write what? MB. And then I must just say MBN, right? MBN. So that will be half AM times H all over half MB times H. Where do I get the H? I'll just put a nice H there. Ooh, just that it doesn't want me to show. Let me put an H. So a nice H there, and then this one I'll call it K. Then you would be proving it nicely and fast. AM over MB. Then you go to, again, the area of triangle AMN again, over. Now this one says NC on the bottom, so you're gonna say the area of triangle NC, but NC what? NCM. Okay, then you would have half. Now the base here is gonna be AN. Remember, you're looking at the other side, so that will be AN times K over half NC times K. then you'll have AN over NC. Then remember that these two are going to be equal, right? You tell them the area of triangle MBN is equal to the area of triangle NCM. Remember, same base, same height, and then between what? Between parallel lines. And then you then say, therefore it means the two fractions are equal over area of triangle MBN. Remember, I'm just moving fast because we did this already, guys. I'm hoping if I'm losing you somewhere, please do tell me. So this one would be area of N triangle NCM, therefore AM over MB would be equal to AN over NC. 5 marks. Next, they give you this one. So let's remember, here it's just our Mercedes-Benz, right? Construct there, and then you join these two. Remember, join those two. Then once you have it like that, what do? Remember to say P1, P2, T1, T2, and then A1, A2. Then you have O1, O2, O3. So remember here you're going to get O1 first. You can say this X, X, Y, Y, Z, Z. So remember you're going to get the expression for O1, of which O1 will be 180 degrees minus 2Y. But then you're going to add all of these in the bigger triangle, right? So remember you're going to get 2X plus 2Y plus 2Z being equal to 180 degrees. Then remember you're going to say I want 2Y. So I'm going to say 2X plus 2Z is 180 minus 2Y. Now you take a common factor, X plus Z is equal to 180 minus 2Y. Now X plus Z is what? X plus Z is actually X plus Z gives me PTA. Oh, but be careful. They wanted you to prove that they wanted PAT. Ne? So if they want PAT, guys, and they are talking about POT, I should not. Let's look at POT. POT. Oh, so I was supposed to make O2 the subject instead of O1. Do you see that? POT is this one here. It's O2. So we're supposed to make O2 the subject, okay? Instead of, I made POA, I don't know why. So you'd say O2, right? Angle O2 is 180 minus 2Z, right? And then you're gonna add all of them, by the way. 2x, 2y, 2z is 180. Then you take 180 minus 2z that side, so that you have 2x plus 2y is equals to 180 minus 2z, right? Then you take 2 as the common factor there, it will be 180 minus 2z. Now x plus y, it's PAT, right? That will be 2PAT is equal to O2, of which O2 is your POT. Okay, so I was showing you questions from previous papers so that you can take note. How do you identify the angles that you are supposed to make, which one you must make the subject? Okay, so here you would make POT the subject instead of O1 and O3. I hope that is clear, but the solution is gonna be the same. So here in the diagram, you are given that you have a tangent. The moment you have a tangent, let's remember tan perpendicular to what? To radius. So here you are given this. So remember, you are going to have your Mercedes-Benz logo again. Mercedes-Benz, Mercedes-Benz. Then you label again, right? 1, 2, 1, 2, 1, 2, right? X, X, Y, y, w, w, o1, o2, o3. Prove a theorem which states that the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment. IE means, that is to say, BCE. Where is BCE? BCE, meaning this angle here, right? We need to prove that it's equal to angle A. So here you are going to write that you can call this C3, right? So remember, you're going to say OC, remember, is perpendicular to DCE. Why? This is because of tan perpendicular to radius. So it means that what does it mean? Oh, now I'm not writing it nicely. We actually even okay, so what I wanted to say is that once you have joined these and you know that this is 90 degrees and then you're gonna have C1, C2, C3, I wanted you to say OCE is 90 degrees, okay? OCE is 90 degrees. Why? Because tan perpendicular to rad. And then say OCE is made up of what? C2 plus C3. Both will be 90. Now you would have labeled that maybe this is X and X, right? And then this is Y and Y. And then here maybe you have W and W. So remember, it means that C3, which is BCE, right? C3 would be equal to what? C3 would be 90 degrees minus the X. Then after you're done doing this, remember it's a matter of adding all the angles in the triangle, okay? So it means you're going to have 2W, 2X, 2Y being equal to 180. Sum of angles in a triangle. You divide by 2 throughout. W plus X plus Y is what? 180. But, oh, sorry, it's 90, right? But you need 90 minus X. So you take the X to the other side. W plus Y will be 90 minus X. What is W plus Y? W plus Y is your angle A. So your angle A is equal to BCE. I just skipped the other parts, guys, that you know already, right? That long part whereby you are saying you join, let this be X, Y, and Z, right? I just wanted you to show to show you the most important parts. Hope you're still following. And then this one is the similarity one, isn't it? So for the similarity, remember on this bigger one, you see what they already give you. This is what I wanted you to see, Mr. Liema. They already give you that the angles are equal. Because the triangles are similar, so they already give you that they are equal. So we just have to tell them given, instead of saying from similarity to anything. But usually I just like from similarity. So here what do? Remember, you have to prove that AB over PQ is equal to AC over PR. So what do? AB. So it means that you are going to mark off on this one, right? No one will penalize you for marking off this one. Or if you still want to work on the bigger one, you can still do that. But though it would seem a bit unrealistic that you can say this big triangle can fit here. You see, it will be a bit unrealistic. So you can still work here and say mark off V on PQ such that VP is equal to AB. Then mark off T on PR such that PT is equal to AC, and then you join them, right? Then after that, what are you going to say? You're going to prove congruency, right? And say what? In triangle ABC and triangle VPT, angle A, you can even start with angle A is equal to angle P. Why? You are given there, so you give them, tell them I'm given, and then after that you say what? You are going to say VP is equal to AB, and then you're going to say what? By construction, right? Construction, and then you're going to say PT is equal to AC. You tell them by what? By construction, right? Then from this you then say therefore triangle ABC is congruent to triangle VPT. Then you tell them side angle side. Then after doing that, what do you say to them? You say to them, remember, is now the angles part, right? You tell them that angle B is going to be equal to PVT, ne? To say this one is going to be equal to that. Why? You say from congruency, remember, from congruency. Then you say this is also equal to this one, right? So you tell them angle B is also equal to angle Q, where from, but it's already given though. You can say from similarity or given, or what, it's already given. Then you can say therefore these two must be equal. Remember our arrows, it means these two must be equal. So you say therefore PVT must be equal to angle Q. You can even tell them that it's because both are equal to B, or what? Both are equal to angle B, the one that is where the lines are coming from, or what? Then because of this, you then say therefore it should mean that, or that I can write that this implies that VT is parallel to QR. Why? The corresponding angles are equal. Okay, so it means this is parallel to that. Then you say therefore you want to say PQ over AB, ne? I also want to say that, ne? I also want to say PQ over I get it's PQ over PV, as we were doing on the last one. Remember when that we were proving, we said on the same side you're gonna say PQ over PV, but in this case, right? Okay, write it. PQ over PV is gonna be equal to PT, ne? Over, oh no, PR over the constructed one, PT. Please tell them this because of line parallel to one side of a triangle. You are using the proportionality theorem, so please tell them that. Then you say therefore this implies that PQ, remember PV, we said it's equal to AB, so you have AB here, and then PR. PT, remember it's equal to AC, so you must have AC. But then you see here they're inverted, ne? So I'm going to say therefore it means AB over PQ is equal to AC over PR. You just switch them, okay? Still the same thing, just switch them, then you get your full marks. I skip the part for construction, hoping that you remember that. Okay, then here is still the Tan-chord theorem, right? And then here is the proportionality theorem, right? Then that brings me to the end of today's session. Are you still there, guys?